This is the 39th lecture of the course MTH 204A for section B. Recall that in the last lecture we were talking about the canonical decomposition of a finite dimensional representation of a finite group. So as usual our setup is as follows, that we are working with a finite group G and assume that Wi, phi Wi, rho I. So these are the up to isomorphism, these are all mutually non-isomorphic irreducible representations over C, of course finite dimensional as I just said, and we denote the character of rho I by chi, and of course let us let Ni stand for the dimension of Wi. Okay. Now let V rho be a finite dimensional complex representation of so it's not it is any finite dimensional representation, not necessarily reducible. Okay. Then by Maschke's theorem on complete reducibility, we do have the following, that there exist subspaces U1 up to UL. So each UI is G invariant and furthermore irreducible. So what it means is the subrepresentation of rho on this UI. So by the from now onwards, at least in this course, for whenever we are having a subspace, I think I should do that here. So if let us say U is a subspace of V, then by rho U I mean the representation. So is a G invariant subspace. By this I mean the subrepresentation of rho. So certainly it is defined as is saying a rho G restricted to U. Okay. So this is the general notation which I will be using in this course. So and here is irreducible. Okay. Then so in this decomposition there could be there could be two summands for which the corresponding isomorphisms are the corresponding subrepresentations are isomorphic. So what I mean is it's not necessarily we should have all this subrepresentations non-isomorphic. There could be several subrepresentations which are isomorphic. Yeah, so it's not necessarily any two subrepresentation here will be non-isomorphic. So there could be isomorphism, there could be summands here which will be isomorphic. So therefore what we can do is we can always collect together the isomorphic subrepresentations, so and write it in this way. So I will just relabel things in a convenient way. So let me do it in this way: U11, U1 R1, U21, U2 R2, it goes on. So here we have used L, we have used K, so maybe we can use M. So U M1, U M UM1, UM RM. Okay. So what's the assumption here? For all I from 1 up to M and j from 1 up to Rm. So given any I from 1 up to M, and for that I if we take j from 1 up to Rm, okay, I think I should put it in this way: the subrepresentation okay. So what I want to mean is in each cluster any two summands, the corresponding subrepresentations will be isomorphic. So the subrepresentations of this Uij is same as subrepresent u I j prime for all j and j prime of I 1 up to m. So, it is R I, okay. And so, it just says that if we take any cluster, then any two subrepresentations, say for any two summands, the corresponding subrepresentations will be isomorphic. And if I take a subrepresentation from one cluster and another subrepresentation from another cluster, then of course they are not going to be isomorphic. So, for let me put it in this way, for all I and I prime with I not equal to I prime, then rho u I j of course non isomorphic to rho u I prime j prime for all j prime belonging to 1 from R I and j, okay, j from 1 up to R I and j prime from 1 up to R I prime, okay. So, this is just this just says that here we have clubbed the summands together such that like clubbed the isomorphic, I mean clubbed the summands together for which the subrepresentations are isomorphic. Anyway, so okay, then further relabeling, what we may assume that, so each of this so here, so what I mean is this let us say here this any, if you take any subrepresentation corresponding to here, let us say u11, so u rho, so this subrepresentation, so this is irreducible, so therefore it will be isomorphic to some of these rho i's, right. So here by relabeling I can assume that this is isomorphic to rho 1. Similarly, I mean here we can by relabeling we can assume that, so m1 is isomorphic to rho m. Of course here m has to be less or equal to k, okay, because up to isomorphism we have just assumed there are only k such possibilities. All right. So now what we do is let's define, so for each, so yeah, I can in fact do it for each I from 1 up to k as well. From each I from 1 up to k, let me define the following operator from V to V. How is that operator defined? This is defined as Ni divided by order of G, G in G, chi G bar times rho G, okay. So this is how we define an operator. So this is a linear operator from V to V, okay. Now what we do is we will so okay, so there should be some I here, of course, so I, okay. So corresponding to each I, thus we have an operator. Now my claim is that these operators are projection operators. So okay, let me go in this, let me argue in this way, that so here you see that the way this operator is defined, I can simply restrict, okay, restrict this operator on any the ui, on any, okay, I should say uj, okay. Remember, just assembling this uj's up to isomorphism, we get this. So once we restrict this operator pi on this uj's, what we see is like since uj is G invariant, so therefore by the restriction is nothing but this operator. So ni by order of G, G is in G, so chi I G prime, and we want to restrict, right. So basically this is going to be this UL, and according to our like according to the notation that we have set there, this is nothing but rho u j g, right. Again let me repeat, I want to restrict this to u j. So that means, so each of these maps operators are going to be restricted to u j, but the notation that we have already adopted, in view of that we can simply replace it as follows, replace it by this, okay. All right. So now what about this fellow? This is an irreducible representation by our hypothesis. Therefore, what we are going to see is one of the crucial observation that we have made while proving the distinct character irreducible characters form an orthonormal basis. We see this is nothing but some scalar multiple of identity. And what is the scalar multiple? That also we observe without any difficulty, that here it will be ni times the dimension of uj, ni times the dimension of uj, and then followed by the character of this, chi, let me for the timing write it like this, the character of this representation followed by chi I, okay. So this times identity, all right. So now what about this quantity? This is an irreducible character, so therefore this must be isomorphic to one of these, right. So this must be isomorphic to one of these. So so this character must be equal to one of this chi i's, So here for this I, if it is equal to chi I, then we have, okay. So here we have two cases, let me do it. So in one case it could be 0, that is when this character is not equal to chi I. So if, let me put it very clear in clear terms, if rho uj is not isomorphic to rho I, then this guy is going to be 0, and otherwise what you show is this quantity has to be like 1, and in that case, so since in the other case these are going to be isomorphic, so the dimension of uj must be same as dimension of the representation rho I, so which is ni. So in that case this factor will be 1, right. So thus what are the possibilities corresponding to this operator? Either it will be the completely 0 operator, and the restriction in this operator will be completely 0 depending upon whether rho I is isomorphic to this sub representation, or it will be identity, it will act as an identity, okay. So we are going to use this observation here. So we restrict this operator. So first we fix an I, then look at the operator pi. Now we restrict pi on each of these subspaces, okay, on each of these subspaces. So for example, if we take just I equal to 1, then when we restrict p1 on each of these subspaces, what we will see is that, like according to our assumption, when restriction of p1 on each of these subspaces will be 0, right, that is what we have observed, and here on each of these subspaces it is going to act like identity. So let me do it in this way, let me write this cluster as V1, this cluster as V2, similarly this as Vm. So what we see thus is, so V1 is the direct sum of these subspaces, on each of these P1 acts like identity, therefore P1 will be identity on V1 and 0 upon the rest, okay. Similarly let us take P2, so P2 once we restrict that here, so restriction of P2, so remember this is the assumption that we are having. So if I take two summands from two distinct clusters, their corresponding sub representations are non-isomorphic. Therefore, like if we take P2, So, yeah, if we take P2, then here the character is chi1, right? Here, so here the subrepresentations are not isomorphic to rho 2, therefore, and not here the character of each of the subrepresentation is chi1, so but in P2 we have chi2, therefore, exactly I mean by as I said in the same logic, there is nothing, no difference. Restriction of P1 upon all of these will be 0, but here upon all of these summands in the second cluster it will be identity, that results in P2 will be restriction of P2 on V2 will be identity, and also and for other clusters it will be 0. Okay. So out of all these what have we got is very simple, that each Pi is, so Pi is identity on Vi and 0 elsewhere. So what, and 0 on every other, on all Vj j not equal to I. Okay. Well, here it is appropriate to say this when I is up to m, but however if we take like so what I have just written, that is identity upon Vi, this holds only when I is up to m, but if I is beyond m, like somewhere between m and k, then trivially Pi is 0 upon all the Vi's, sorry, yeah, so Pi is V0 upon all the Vj's, because I is there in that scenario, this I is beyond m. So thus what have we obtained? Let me put down everything together. So what we obtain here is very simple. If we let V belongs to V, since we have this direct sum decomposition, V can be written as small v1 up to small vm, where each Vi belongs to capital Vi, right? And in this case what we do is apply Pi upon V, okay. So this is, it will be Pi of V1, so Pi of Vi and then Pi of Vm. So what we have just observed is here only this term will survive and rest will go to 0. So therefore what do you see, that for each V, Pi is sending V to the ith summand of the decomposition. What is the decomposition? Let me again remind you, by clubbing the isomorphic summands together. What I mean by this, the corresponding sub-representations are isomorphic. This is what we get, and we see that each V, given any I, it is sending each V from V to the ith summand. So therefore thus this Pi is nothing but a projection operator. Try to understand. So like if V is already from Vi, then certainly, like we have already seen, right, that Pi is identity upon Vi. So it is a projection operator upon V such that whose image is Vi, right, whose image is Vi. That is what we have seen, right. It is 0 upon all other summands and identity upon Vi, so it is a projection operator. So therefore let us come to the main point, that is the observe that this Pi, in the definition of Pi, what is there? Pi just involves the irreducible characters which are already chosen, which are already given, and the given representation. Apart from that, it does not contain anything. What I mean by this is, the point that I want to stress upon is, look at the definition of PI. This entirely independent of the decomposition that we are working with. Okay, it's entirely independent of the decomposition that we are working with. So in other words, if another person starts with a different decomposition and then he clubs together all the isomorphic copies and then form the VIs out of each of the clusters that he has obtained at the previous stage, then he will also obtain his VIs are going to be the images of these projection operators. Okay. So I repeat that, like as I said, the main issue is, suppose let us say 5 people are given the same representation and asked to find these VIs. Okay. So how these VIs are obtained? Let me again remind you that each of them will start with his or her own decomposition and then cluster and then take the appropriate clusters. Okay. So whichever decomposition they work, so it's independent of, like, whichever decomposition each of this person is choosing, at day end the VIs that he or she is going to get is same as that of others, because we see that from any decomposition the VIs that you obtain, those VIs are going to be the image of these projection operators. So remember that this projection operator only involves the characters and the given representation. Okay. So like whenever a representation rho is given to us, we immediately form these PIs and take their images, and therefore we know that, like, these images of these projection operators are going to be there in whatever each of these 5 persons have done. Okay. So this shows VIs are unique, because VIs are solely determined in terms of the irreducible characters chi I and the given representation. So even if these UJs are different, at day end the VIs that going to be they are going to see will be the same. Okay. So this shows the VIs unique, because VI is because they are the images of okay. I would again try to stress on the fact that the difference that the given a representation, the decomposition into reducible ones, that decomposition need not be unique. Of course, it need not be unique, but in the decomposition that you have taken, when you take the appropriate clusters, namely when you collect the isomorphic ones together, then after collecting isomorphic ones together, then these VIs that you obtain, these are going to be unique, because they are solely determined in terms of the representation and the characters of G. Okay. So therefore, though this is basically of course this decomposition is coarser than that of this, because here it is, here there is no, this VIs may be reducible. So given a V, there is given a representation, so these VIs need not be reducible, they could be reducible. So therefore this decomposition that we are talking about here, this is of course more likely to be coarser than the irreducible ones. However, the advantage here is they are uniquely, so this decomposition is unique, okay. This is not the finest one, however, this is going to be unique. So in the light of this, what we can say is the following, that so since these VI's are uniquely determined in terms of PI's, so another way of decomposing a representation into irreducible ones could be the following, that in the first stage what we do is, whenever this row is given to us, we immediately form these operators and look at their images. So from whatever we have done, we know that the subspaces that we obtain from these operators, they are going to form a decomposition like this. This follows from the general follows from this general observation that we have just made, that is, given any representation V, if we construct immediately these PI's and look at their images are going to give us a decomposition. So once it is there, again from the general theory we know, for each of these V1s, so each Vi can be further decomposed into irreducible subspaces and they will be isomorphic to each other. So in the first step, using the PI's, we may first decompose rho, okay, and then in the next step we can further decompose each Vi into irreducible ones, okay. So thus this in the light of this general discussion on the light of this canonical decomposition, we have another way of reducing our representation into irreducible ones, okay. So let me again stress upon that. So what we have done earlier is that we start with any decomposition into irreducible ones, then collecting things together, we obtain something which is where the summands are unique. So this is what we call canonical decomposition. So canonical means it does not depend upon the choice. Canonical decomposition of rho, okay. This is what we do. Starting from the irreducible ones, we get the canonical decomposition, but while doing that we see this summands are uniquely determined by PI's which are of this form. So that also tells me that if we are asked to decompose the representation into irreducible ones, we can take the following alternative way, that is we first construct these PI's and from that we obtain these VI's, okay. So at the first stage we directly obtain the canonical decomposition, okay, right, because like the images of PI's are bound to give us this decomposition in view of the that is what we have, that's what we have discussed so far. It's a very general phenomenon. So therefore at the first stage we directly obtain the canonical decomposition, and in the next stage we can further decompose each and every sub-representations corresponding to Vi into irreducible ones, and therefore that we finally obtain some decomposition into irreducible ones, okay. I think this is more than enough just to give you an just for the sake of completion, or maybe it will be easier to see maybe this, okay. Let me first do it. So this is what the general theory we have discussed on canonical decomposition. Now let us just revisit the example that we have discussed in the last lecture, just to motivate, just to show you how to prove the uniqueness. So let me revisit that again. So what was that? So there G was the very simplest one, Z modulo 2Z, so which is basically plus minus 1. You can simply take the multiplicative group of plus minus 1, that's same as that, okay, multiplicative plus minus 1, and this group has 2 one-dimensional characters. So what are the characters? One character is sending 1 to 1, both plus minus 1 to 1. This is one character, another character is, say of course plus 1 has to be sent to plus 1 and minus 1 has to be sent to minus 1. So basically the identity inclusion. So this is there. So what's the character here? So here the character is the trivial character and here it is a non-trivial character. Then given any representation of this group, finite dimensional representation, what we can do is that, so what are the PIs in this case? I mean just to, like why do we look for examples? So whenever we have some general theory, we always revisit some concrete examples in the light of this theory. So just to see whatever is happening, and that makes our understanding better, because examples are the best guides for any theory. So here for example this P1 is nothing but, so here each Ni is 1 and order of G is 2, so half times. So the first one will be for example the trivial one, so identity plus row of minus 1, okay, and the P for P2 is identity minus row of minus 1, okay. So what is image of P1? So image of P1, you see it is nothing but, so like let me do it here, image of P1 is the, so eigenspace, so this is basically all such V in V such that rho minus 1 V is V, right. So if you apply rho minus 1 on any, so the P1 V will be V plus rho minus 1 V. If you apply further rho minus 1, you will obtain it is going to be fixed, and here it is going to be the opposite one. So basically like here we have only two operators, right, rho 1 and rho minus 1. Rho 1 is identity, so that is not going to play any role at all. So the only effectively we have exactly one operator, and for that operator we can concretely see the VIs which are going to appear in the canonical decomposition. So these are nothing but the eigenspaces of, so this image of P2 is this is the, which we have defined as V minus 1, okay. Okay. So another way of looking at this, as I said, we essentially have exactly one operator, rho minus 1. So rho minus 1 is something which is having this property. So therefore rho minus 1, its minimal polynomial is, so its annihilating polynomial is x square minus 1, that is x plus 1 into x minus 1. So like therefore V is going to be kernel of this, so that is so like kernel of this is that corresponds to the eigenspace having eigenvalue minus 1 and this eigenvalue plus 1. So the thing is the decomposition that the decomposition of V what you obtain the primary decomposition theorem is basically the canonical decomposition for this representation, okay. So I just wanted to show that in this example this decomposition is actually same as some decomposition that you have, it coincides with something that you are familiar with in linear algebra. But however, if the groups are much more complicated, then maybe we cannot expect that, because if they are essentially more linear maps, then things will be certainly much more delicate. But in this case, this canonical decomposition coincides with the original primary decomposition correspond to that operator. Anyway, so enough of canonical decomposition. I should now move on to something else. So we now aim to prove the dimension theorem of representation theory of finite groups. So what it says is the following, that so as usual we are working with a finite group G. right, and let this V rho be an irreducible representation, be an okay, yeah. So this be an irreducible representation over C, of course finite dimensional. Okay. Then the dimension theorem says that this dimension of V divides order of G. Okay, we will prove this theorem. You see, this is a very from the statement itself, you see it has to be a very influential theorem, because earlier we have found that we have some relation like this, where these are the well, I think to begin with I should fix that, what I always do, finite group, and Wi, rho I from 1 up to k are all isomorphism classes, are all irreducible representations over C, irreducible of course finite dimensional over C, and non-isomorphic. What I mean by this is, if we take rho I and rho j, I not equal to j, they are not going to be isomorphic. So and here also we take n to be dimension ni to be dimension wi. This is what we have. Let's keep that fixed throughout. So earlier we have seen that we have this relation. Then dimension theorem further says that, each of these ni's must divide order of G. So earlier looking at this, especially when G is order of G is small, you see that even this relation shows that the choices of ni's are actually, when order of G is small, then choices of ni's are a few, and then now this further condition in fact sometimes uniquely yields uniquely yields precisely all possibilities for ni's. Okay. Earlier even earlier it showed that we are only a few possibilities. Now sometimes this observation that sometimes uniquely yields all the that sometimes yields us exactly all the ni's. Okay. So let me first give you an example, then you will understand what I am talking about. So we will prove this theorem, but later on we see some let me talk about the applications, a few applications of this, which will show us that the aim is to tell you to realize that this is a very this observation together with the earlier one, that is sum of squares, that indeed yields us exactly all the irreducible representations, right? And having irreducible representations is if you have knowledge of all the irreducible representations of a group, then from that we know we can think. From that we know that we can actually study any given representation, because any given representation is a direct sum of the irreducible ones. So first let me talk about this case when G is order of, so P is a prime. Okay, P is a prime. So like in this case, n k square will be P square. Okay. In view of the dimension theorem, each ni has to be P. So therefore, what are the possibilities? So, but we do have a trivial representation. So one of these ni's must be, one of these ni's will be 1, because always for any given group the trivial representation is a irreducible representation, which is non-isomorphic to any non-trivial representation. So therefore, like this means, what are the possibilities here? Either one of these ni's is P and rest are 0, Okay, but that does not but that possibility does not happen, because like, okay, I think I should put it here. So there are only two possibilities, either k equal to 1 and n1 is p, or k is greater than 1, and there in that case each ni is 1. These are the only two possibilities. But this cannot happen, because as I said, the trivial representation is already included in this collection. So therefore, like one ni must be 1. So certainly, therefore this does not happen, we must have this. So therefore we see each ni is 1. So what does this mean? This has all irreducible representations are of dimension 1, and that actually tells us something very interesting. I think we should do that as a separate theorem. We should do that as a separate theorem. What it shows is very simple thing, that okay, this is for any group G, finite or infinite. Right now I don't insist this to be finite. For any group G, the following holds. What are the following? G is abelian. Every reducible representation over C is one dimensional. Okay, this is what we obtained as Schur's lemma. Now when G is finite, the converse also holds. So this is there and G is finite, then this implies G is abelian. Okay. Why is this true? This is simply because of, in this case you just apply this dimension formula. So in the scenario each ni will be 1. So therefore it forces k has to be order of G, same as order of G. And what is k? K is same as the number of conjugacy classes. So that it shows that the G has exactly these many distinct conjugacy classes. So that means the conjugacy class of the conjugacy class of X is exactly singleton X. When is that happen? When does that happen? So G has exactly these many conjugacy classes. So that means it forces, this is what we have happen, and this means that like each X is in the center. That means the group has to be abelian. So this is a very general phenomenon. Now in view of this, you see that here we conclude G is abelian. So of course you may say that we haven't got any new result. We have already proved every group of order p squared is abelian. That's true, but here it is. Here also we obtain the same result in view of this representation theoretic results. So this is the we obtain the same result. This is like another way of order representation theoretic way of proving something that we are already familiar with. Okay, the result is nothing new, but however my intention was to show you that how this theorem can be, I mean it is useful. So another example I should also give, that there will be, so as I said that this earlier formula on square of sums together with it, that exactly gives us all the, and that exactly gives us all the irreducible, at least the dimension of the irreducible representations when order of G is small. So let me do it here. Let me consider this case. P this let this be 2p. So like P is a prime. So as expected, we have this scenario. Okay, this scenario. So what are the possibilities? So this is 2p. Okay, this is 2p, and one of this factor is, of course, it has to be, one of the ni has to be 1. So therefore basically like this, let us say if I take n1 equal to 1, because by relabeling I can always do. So then this is what the scenario we are having. Yeah. Okay. Now so what are we left with here? Can any of these in this scenario, can any of these be P? Like can any of these be P? Certainly not, okay, because then the left hand side will be more. So therefore what's the situation? So each of them will be either 1 or 2. So one thing is clear that in this case any reducible representation will be either 1 dimensional or 2 dimensional. Now we want to know how many 1 dimensional characters will be, 1 dimensional representations will be there, and if we can say about anything about the number of 1 dimensional or 2 dimensional representations. So that also we can say in this situation. How? So like okay. So let me do this in this way. Let me do this in this way. Like here, let me get back to the original form. Okay. So the claim is, so number of 1 dimensional representations, cannot be so like as I said that each ni is either 1 or 2 here. Each ni is either 1 or 2. So each 1 dimensional can yeah. So number of representation cannot be 1 or P, right? Because if so, then what will happen that, so let us take the like the first case. So therefore here, so all each of this, so this is 2p minus 1, right? So therefore like I mean k cannot be 1, because p is a prime. This is at least 3, k cannot be 1, and hence from in this like k has to be greater than 1. So therefore all apart from the n1, by assumption here, all these ni's. So in the first case, so this is actually obvious. The first case we must have 2 square sum of this will be 2p minus 1, right? Because as I said that in this case k has to be greater than 1, but this is certainly not allowed to happen because this side is even, this side is odd, and in the later case, so then we have like we have exactly p terms here which are equal to p. So thus, so let us say sum of if I rearrange this ni's, so n p plus 1 up to nk has to be p. You see what I am talking about is if there are, let us say, exactly p number of terms here which are 1, so that in that case, so left hand side will be p plus something, right hand side is 2p. So therefore k cannot be equal to p. So hence the rest of the terms, these are all squares of 2's which will be equal to p, which is again not allowed. Okay. So thus, so the number of 1 dimensional representations cannot be 1 or p. So there are exactly 2 possibilities then. It has to be either 2 like or whole 2p. So therefore either all representations are all irreducible representations are dimension or one dimensional or we have exactly two of them are one dimensional and p minus 1 by 2 yeah. So, p minus 1 by 2 are two dimensional because sum has to be equal to 2p, yeah, sum has to be equal to 2p. So, let me see whether I have yes. Okay, I just made a small thing I should have said, I am sorry. So, what about the number of one dimensional representations of a group? So, every one dimensional representation, so this observation we have already made, recall that like number of one dimensional representations of a finite group G. So, all representations are complex representations. G is same as order of G modulo G prime. This is already we have observed. The main reason, again let me just tell you that so a one dimensional representation is basically a homomorphism from G to C star. Therefore, there is a commutative diagram. Okay. So, what I mean by this is every one dimensional representation, let us say something a representation of C is actually obtained by a one dimensional representation of G modulo G prime to and composing that with the quotient map. Okay. So, every one dimensional representation of G is obtained in that way. Okay. And so, therefore, like distinct one dimensional representations here. So, the argument is very easy, we have already observed, just I just want to remind you that. So, like if we have two distinct one dimensional representations here, they will yield to distinct one dimensional representations of G modulo G prime and vice versa. So, therefore, number of one dimensional representations of G is same as the number of elements in G modulo G prime, which has to be divisor of G. So, in this case we are only only 4 divisors of G, 1, 2, P and 2P, and from that we see this cannot be 1 or P. So, therefore, one dimensional representation. So, there are only two possibilities, either it is the number is 2 or number is 2P. So, in the first case all reducible representations are one dimensional, and in the second case 2 are one dimensional and rest must be of 2 dimension, and then of course then using this sum. So, like like as I said that yeah. So, we have exactly two one dimensional representation, and since we have this sum formula that immediately force that we should have only P minus 1 by 2 or 2 dimensional in this case. Remember that. So, when we have only 2 one dimensional representations, so that forces that P has to be an odd prime, because if P is even prime, then that falls, that falls already in this category. So, if we have only 2 reducible representations, one dimensional representations, then the group must be non-abelian, right. P must be odd in particular, and therefore P minus 1 by 2 is an integer, and we have exactly these many 2 dimensional representations. Okay. So, like you see that this formula, when it is coupled with this dimension theorem, So, when order of G is something special or order of G is sufficiently smaller, then it actually indeed provides us a lot of information about the irreducible, about the irreducible characters, about the irreducible representations representations of the group G. Okay, so maybe today I won't have sufficient time to prove the dimension theorem. So first, so far we just assume dimension theorem and shown some of its applications. Let me first draw a corollary of this dimension theorem. So we assume dimension theorem and deduce that corollary, which is also an interesting one. As I said, I would like to show you. I would like you as I said. So I want you to realize how important and how influential this theorem is. So I will talk about a corollary here. If after that I have some time, certainly I will start the proof of the dimension theorem. So what does the corollary say? The corollary says the following, that it says the following. So no finite group, no finite simple group can have a an irreducible two-dimensional representation. Of course, over C. So, in other words, if G is a finite simple group, then it cannot have it's a finite simple group, then its irreducible representations, either they will have of dimension 1 or dimension more than 2. Okay. So, how to prove that? The argument is very simple. Let me quickly show you that suppose G is such a group, we assume the contrary, that is G is having a complex two-dimensional representation which is irreducible, and therefore that will give us a homomorphism rho. So it's a okay. So what I should do is this GLV, V is a two-dimensional vector space and this is isomorphic to GL2C. So for notational simplicity, I simply forget this part and call this itself as rho, and it's an irreducible two-dimensional representation. It cannot be trivial representation. So that means rho is non-trivial. So from simplicity it follows. So what does simplicity yield? This is either trivial or G. So kernel of rho is G. It means the representation has to be trivial, which is not allowed. So the kernel has, therefore this cannot happen from simplicity. From simplicity, okay. Therefore G has to be therefore rho is injective. So we may assume G is a subgroup of GL2C, okay, because basically instead of G we are taking rho G, which is isomorphic to G. If I can arrive at a contradiction for rho G, then it will be, then that serves our purpose. So we can simply assume for simple G is a subgroup of GL2C, okay. And now one thing is very clear, that 2 has to divide order of G in view of dimension theorem, because our representation, irreducible representation, is having dimension 2. So that means there exists an element, there is an element G in G such that having order 2, yes, such that order of G is 2, right. The claim is this G has to be minus identity claim this G has to be minus identity, and if suppose that we are able to establish this claim, then modulo this claim what will follow is, so plus minus identity is like if we can show G is minus identity, then we see that this plus minus identity, this subgroup is a subgroup of G, right. So like this is a subgroup of GL2C which now contains inside G, and this is of already a normal subgroup of, so plus minus identity is already a normal subgroup of GL2C because it's a subgroup of the center. So therefore this will be in particular a normal subgroup of G as well, because it's already a normal subgroup of the general linear group, and from simplicity will further force G has to be plus minus identity, okay. This will further force G has to be plus minus identity, of course modulo this claim, and so then it's a problem because if this happens, then G becomes abelian. So since it's abelian, it cannot have a two-dimensional irreducible representation, so that contradicts the hypothesis. Once we obtain, so since we have to begin with, we have assumed G has a two-dimensional irreducible representation, so G cannot be abelian. So but this forces G to be abelian, so contradicting the hypothesis, okay. So now everything rests upon this claim. So I think it is now clear that if we can establish this claim, how that finishes our proof, because if G is minus identity, then we obtain this normal subgroup of G. So by simplicity this has to be G, that forces G to be abelian, but since we have assumed it has a two-dimensional representation, complex representation, certainly the group cannot be abelian. So this actually contradicts with our hypothesis, okay. Now regarding this claim, that is also quite I would say an easy task, because very simple that consider the determinant map. So we restrict determinant map to the subgroup. So therefore determinant map is a, so it is a, so homomorphism from G to C star, right. So homomorphism from G to C star. So it's a homomorphism G to C star. So determinant, the restriction of determinant to G, the restriction of the determinant map to G is thus a one-dimensional representation of G, and we know that every one-dimensional representation must be obtained in this way, okay. So like here we have a map, so f bar of G bar will be, okay, I should say x, f bar of x is simply determinant of x, right, because we have, whenever we are having a map that factors through G modulo G prime. And what's the problem here? What kind of problem can we expect to be here? So like the determinant map, so this, our assumption is G has order 2, okay, fine. So, like try to see this G has order 2, that means G square is identity, right. So, the minimal an annihilating polynomial for G would be x plus 1 into x minus 1. So, thus the possible eigenvalues, so G is a 2 by 2 matrix, complex matrix whose possible eigenvalues are 1 and minus 1. If we can show that the determinant of G, so here I think here I should say that enough to show determinant of G is 1. Okay. So, since the possible eigenvalues of G are 1 and minus 1, it is a 2 by 2 matrix. So, if we can show determinant of G is 1, then if we can show this, then automatically it will G must have all the eigenvalues minus 1. So, that is G has to be minus I2. Okay. So, in order to show this, we should show determinant G is equal to 1. Now, therefore, we now consider the restriction of the determinant map to the subgroup G, and now we have this scenario. But what about G prime? G is simple. So, G prime must be, so like G prime must be the trivial or whole of G, right. G prime trivial means G is abelian, but again you see that, like, since we assume G has a 2-dimensional character, G cannot be abelian. So, therefore, G prime has to be G, as G cannot be abelian. Okay. Therefore, this is actually trivial group. So, this is actually trivial group. So, therefore, like if we start with anything here, it has to go to, so I say what I see, okay. So, determinant of G is thus f bar of G bar, since this is a trivial group, this has to be 1. Thus, we are done. So, let me again summarize the proof, and with that I will finish. So, the claim was, if we are having a finite simple group, then it cannot have a 2-dimensional irreducible representation. Okay. So, say assume the contrary, therefore, assume the contrary, that immediately shows G cannot be abelian. So, from the simplicity tells us that we can assume that G is included inside GL2C. Dimension theorem here provides us with an element inside G having order 2. I want to show that element is minus identity, because if it is minus identity, then we do have this subgroup of the center which becomes automatically normal inside G, but therefore that forces again G to be abelian, which is a contradiction. So, to show that this is minus identity, it is enough to show its determinant is 1, because for this G the eigenvalues are only plus 1 and minus 1. Okay. So, like G is non-identity being order 2, and if you can show the determinant is 1, since the determinant is the product of the eigenvalues, here you can see G is diagonalizable, right. So, this G is diagonalizable. So, the product of diagonal elements will be the determinant, elements are plus 1 and minus 1. So, determinant is 1 means either both the eigenvalues are 1 and both are minus 1, G is not equal to identity by assumption. So, therefore, both the eigenvalues will be minus 1, that results in G to be minus identity. So, it is enough to show determinant of G is 1. And now next observation, in order to show this, we observe that, so determinant, if we restrict that to G, that works as a 1-dimensional character, that is a 1-dimensional representation. Therefore, this will factor through a 1-dimensional representation of G modulo G prime, but that is some simplicity, that is a trivial group. So, therefore, that shows this. Okay. That shows determinant map, the restriction determinant map on G is identically trivial. Okay. I think with that I will finish. So, the next lecture I will give a proof of the dimension theorem, okay, and then we will go ahead. Okay. So, with that I finish this lecture.